Okay, question 7 says, find a parameterization for the curve described, include an interval for the parameter values. And part A says the left half of the parabola y equals x squared plus 1, originating at the point 0, 1. So you see up here the left half, this parabola y equals x squared plus 1 in green. And since we originated at the point 0, 1, at t equals 0, we're located right here, which is the vertex of this parabola. And then as t increases, we're going to move along the parabola in this direction as indicated by these arrows. Okay, now if I think about the horizontal motion of this tracing point, well, we're moving to the left. And so x is a decreasing function of t. And so for simplicity, I'm going to go ahead and set x equal to negative t. So for example, let's say 3 seconds after I start my timer, I'm located at this blue dot. Well, what would x equal? X would equal negative 3. Okay, so more generally, t seconds after I start my timer, okay, the x coordinate is going to be negative t. And so how would I find the y coordinate? Well, I'm going to plug negative t in for x in the equation for the parabola. And if I do that, I get negative t squared plus 1, which is equal to t squared plus 1. Okay, so t seconds later, my tracing point has coordinates negative t and t squared plus 1. And down here, I've just included the graphs of x and y as functions of t separately. All right, so in conclusion, here is a parameterization for the left half of the parabola, y equals x squared plus 1, that originates at the point 0, 1. Okay, cool. So let's check our answer on Desmos. Okay, so here, the parametric equations, so negative t for x and t squared plus 1 for y. And t is greater than or equal to 0. Desmos wants an upper bound, so I just put in 20 because it's fairly large. And here's our tracing point. You can see when a is 0, we're located right here at 0, 1, right? And if I hit play, I can see I'm tracing out the left side of that parabola, so it's working. All right, cool. Okay, so let's next check out part B. It says the circle x minus 2 squared plus y plus 3 squared is equal to 4, starting at 4, negative 3, and moving counterclockwise with a constant speed of 4 miles per hour. All right, so this circle, right, has radius 2, because I see a 4, which is 2 squared on the right-hand side. And the center of the circle is at 2, negative 3. So you see that circle pictured up above here. And we start at the point 4, negative 3. So when t is 0, we're located right here at this blue dot, 4, negative 3. All right. So first thing to note here is that the distance covered in one trip around the circle is just the circumference of this circle. So this is what? 2 pi r. And the radius is 2. And note that since the speed is given units of miles per hour, it's safe to assume that distances are measured in miles. Okay, if that was not the case, then the problem would specify that explicitly. But here, right, the assumption is that the distances are in miles, and so 2 pi times a radius of 2 miles gives us a total circumference of 4 pi miles. And we're moving with a constant speed of 4 miles per hour. And so the time to complete one trip around would be the distance covered, 4 pi miles, divided by the speed, 4 miles per hour. And this simplifies to pi hours. Okay, so we complete one trip around the circle every pi hours. All right, so now in light of the last few videos, this is really saying that the period of the sine and cosine waves for our x and y coordinates, which is 2 pi over omega, is equal to pi hours. So this implies that omega is equal to 2. Okay, cool. So now let's go ahead for just a moment. Let's think about parameterizing this circle first. Okay, so in other words, it's the same circle, but I've just shifted the center to the origin. We've done a lot of problems like this before. Okay, so what do we now know? We know, right, that we're going to move in a counterclockwise fashion. When t is 0, we're located at this right edge of the circle, which has coordinates 2, 0. And we complete one trip around in pi hours. Okay, so here's a parameterization for this circle. X is equal to r, which is 2, times the cosine of omega t, so cosine of 2t, and y is 2 times the sine of 2t, and t varies over this interval from 0 to pi. All right, so if this is a parameterization of the circle centered at the origin, to get a parameterization of this circle, as we saw in a previous video, I can go ahead now and just shift the center to the point 2, -3. So in other words, I'm just going to add 2 to the x coordinate up here. So I now have x is equal to 2 plus 2 cosine of 2t, and y is -3 plus 2 times the sine of 2t, and again, t varies over this interval from 0 to pi. All right, so that does it for part B. Let's check it out on Desmos like we did for part A. So here are the parametric equations for the circle. Okay, here is our tracing point. When a is 0, you see we're located at 4, -3. And now if I let a vary over this interval from 0 to pi, so I hit play, I can see I'm completing one trip around. All right, cool. Let's now move into part C. Okay, this says the piecewise linear path from the point P with coordinates -2, 3 to the point Q with coordinates 1, 4 to the point R with coordinates 5, 4. All right, so I have a picture of this piecewise linear path. So we go from P to Q and then from Q to R. All right, so let's start out by looking at this line segment PQ. Okay, I can see that the slope of this line segment is 1/3, because if I move horizontally to the right 3 units, I'm going to move vertically up 1 unit, so the slope is 1/3. And then to write down the equation of this line that passes through P and Q, I can use point slope form. So using the coordinates of P, I have that y minus 3 is equal to m, which is 1/3 times x plus 2, which can be rearranged as y equals 1/3 x plus 11/3. Okay, so that gives me a parameterization of the line segment PQ. And so if I choose any point on this segment, okay, let's say x is, roughly about a half, okay, I'm located right here. The coordinates of this point are x, comma, and then y, and y is right here, just coming from the equation of that line, right? So 1/3 x plus 11/3. So for simplicity here, since x now is increasing, I'm going to set x equal to t. Notice in part A, there, the x coordinate was actually decreasing, so we had set x to -t. But here we're moving to the right, so I'll set x to t. So if x is t, then y is 1/3 t plus 11/3. Okay, and since the x coordinate varies from -2 to 1 as we move from P to Q, and since x and t are the same thing, that means that t also varies from -2 to 1. Okay, so now we need to write down a parameterization as we move from Q to R. Well, that's fairly simple, right? Any point I choose from Q to R, let's say right here, okay, it will have coordinates x, comma, 4, right? The y coordinate of all points on this line segment, since it's a horizontal line, is 4. And so, again, just setting x to t, right, we can say that x is equal to t and y is equal to 4 along the segment QR. And here, t, which again is just the same thing as the x-coordinate, varies from 1 to 5. All right, cool. Let's check that out on Desmos. So here is just the 3 points, P, Q, and R. And then here are the parametric equations for the segment from P to Q. And then here's the parametric equations T, 4 for Q to R. And then here, I have to break this up into two tracing points because I have to make this transition. But so if I let A, which is the parameter for the tracing point from P to Q, vary from -2 to 1, okay, if I hit play, I see that takes me from P to Q, and then I'll go ahead and turn this one on, and I'm letting this parameter vary from 1 to 5, and that takes me from Q to R. Okay, and last up is part D. It says the curve below with the indicated orientation. The curve portion is a semicircle. Your parameterization should have domain from 0 to 10. All right, so I've included the curve up here. So we're going to follow this semicircular path in a clockwise fashion first, and then we're going to follow that with this straight line segment as we move from right to left. Okay, so breaking things up in this fashion here, and one thing to note is that since it says your parameterization should have domain from 0 to 10, that's saying, right, that it's going to take us 10 seconds or minutes or whatever the time unit is here to make one complete trip. What it does not say is how long it's going to take us to cover the semicircle and how long it's going to take us to cover the line segment. So that part is actually open-ended. So for this solution, I'll go ahead and break things up so we traverse the semicircle in, say, 5 seconds, if seconds are the time interval. So in other words, over the interval from 0 to 5. And then we'll cover the line segment in the next 5 seconds. So in other words, over the interval from 5 to 10. But again, you could break this up in any way you like, since the problem doesn't specify the length of time for each individual piece. All right, but in any event, let's go ahead now and check out the semicircle. Okay, so since we're parameterizing a portion of a circle, we can use all of the methods we've been looking at for parameterizing circles in the last couple videos. Now, the one thing to keep in mind here is that since we're looking at a semicircle, and we know we cover this semicircle in 5 seconds, that says that the half period, where here the period's in reference to the sine and cosine waves of our x and y coordinates for the semicircle. So the half period is equal to 5 seconds, right? And the full period is 2 pi over omega, so half of that is equal to 5. So this implies that omega is pi over 5. Okay, now the radius of our circle is 3. And keep in mind that our starting point here is at -3, 0, so the left edge of the circle. And we want to move in a clockwise fashion. And so I can accomplish that by setting x equal to -3 times the cosine of pi over 5t, and y to 3 times the sine of pi over 5t. Okay, so note when t is 0, x is -3 and y is 0, which is exactly what I want. And then in the next few moments, the x coordinate will increase and the y-coordinate will increase, meaning we're moving to the right and up. And that's going to give us a clockwise orientation. All right, so this is a parameterization for the semicircle. And then, so for the line segment, well, what do we know? There, when t is equal to 5, we're at the x-coordinate of 3. And then when t is 10, we're at the x-coordinate -3. And notice that all points on this line segment have a y-coordinate equal to 0. All right, so this graph here is a graph of the x-coordinate versus time. So as I just noted, when t is 5, the x-coordinate is +3. And then when t is 10, we're down here at -3. And I'll go ahead just for simplicity and connect these by a straight line segment. In other words, I'll set x to a linear function of t. All right, so how do I write down the equation of this line segment? Well, it's a part of a line, or part of the line rather, that passes through the point 5, 3, and 10, negative 3. So using point slope form and noting that the slope of this line segment is what? Well, if I move horizontally to the right 5 units, I move down 6. So this has a slope of negative 6/5. And here I'm using the coordinates of this point 5, 3. So I have that x minus 3 is equal to negative 6/5 times t minus 5, which can be arranged to x equals negative 6/5 t plus 9. All right, so now I'm going to take this out just to make some space. To summarize, okay, here I've just taken this parameterization and copied it over here. This is our parameterization of the semicircle. And then this right here below it is a parameterization of the line segment, right? Again, all points on the line segment have a y-coordinate that's equal to 0. Okay? It's the x-coordinate that's changing, and it's changing according to this linear function. Again, that's just coming from the fact that when t is 5, x is 3, and when t is 10, x is negative 3. All right, so now let's check that out on Desmos here. So here's our parametric equations for the semicircle. T varies from 0 to 5, and then here are the parametric equations for the line segment, and t varies from 5 to 10. Here's the tracing point for the semicircle, so a is going to vary from 0 to 5. So if I hit play there, I see that, yep, that takes us over the semicircle. And now, if I go ahead and let the parameter b for the line segment vary from 5 to 10, that takes us to our starting point. So it works great, and that is going to do it for this video. Thank you so much.